United in AI, we learn and lead, ensuring we always stay ahead. February 2022, Russia launched a full-scale invasion of Ukraine. To support the Ukrainian tech sector, the largest AI community in Ukraine, AI House, brought together global AI experts for a charitable education project, AI for Ukraine, lectures and workshops about the latest in AI and ML in exchange for donations to Ukrainian defenders. This time, AI House teams up with one of the most powerful Ukrainian AI ML tech companies, Roosh, for AI for Ukraine Season 2, to assist Ukrainian AI talents in expanding their network, equipping them with the most current and relevant knowledge in AI and ML, and raising funds to support Ukraine. Join AI for Ukraine Season 2. Harness the opportunity to learn, network, donate, and support Ukraine.
Hi, good evening, everyone. Welcome to the AI for Ukraine Season 2. My name is Timur Tleuberlin. I'll be a host today. I'm co-founder at Desti Labs. It is AI and ML agency where we delivering solutions for business clients that are trying to enter complex AI world. And today we are going to have a session about AutoML. And I hope everyone will enjoy this session because we have a very special guest. It is Lars Kotov. Welcoming you to the stage. Hi, Lars. How are you?
Hey, Timur. I'm good. How are you?
Yeah, I'm fine. I'm fine too. First of all, I want to thank you for participating in that session because by doing that, you're not only helping to spread the knowledge about AI and machine learning in Ukraine and also supporting Ukraine in current battlefield as all the funds that were collected during that session will go to the reactive post. It is charitable organization that supports our defenders. So as a member of AI House community, I want to thank you. And I think that everyone will agree that we are really appreciate this one.
Thanks for the invitation.
Yeah, nice to meet you. So while we are waiting for other people to join, I wanted to ask first of all, where are you right now? Where are you joining us from?
I am joining you from the state of Wyoming in the United States. So I believe it's a 9-hour time difference. So it is still relatively early in the morning here. And it is also very snowy. So not so much this week, but last week it was very cold. It went down to -40, and -40 is actually where Celsius and Fahrenheit are the same. So that's very easy to remember, but not necessarily something where you want to be outside.
Yeah, yeah. I can understand because recently in Ukraine we also had very cold days with a lot of snow and ice, and yeah, it is not the most pleasurable time
Yeah.
to be outside. Yeah, yeah, nice. And also, I wanted to ask you, like, what it is, what do you think about recent news in AI overall in the world? Maybe you heard something about leaked plans of Google on how they plan to conquer AI world. What do you think about it?
Well,
And
it's certainly
overall,
a very exciting time for AI because of large language models and everything that's related to that. And well, I'm being at a university, I mostly think about this in the context of higher education. So, in particular, the challenges that we face because students have access to ChatGPT, so they can just produce an assignment or a solution to an assignment that looks like they did it themselves, and you can't really tell, right? So this comes with challenges, and we are working very hard to find some ways of addressing this, but this is, of course, very difficult, right? So that's kind of where I'm thinking about this at the moment because of the challenges that we're facing at the kind of at the education level. But then, of course, I think this is very exciting in the sense that, well, for example, for the things that I'll be talking about today, for automated machine learning. One of the aims of this is to make machine learning more accessible to everybody and really allow everybody to get state-of-the-art performance in machine learning, even if you're not a machine learning expert. But of course, there are still limitations, and you still have to write some code, and you still have to at least roughly understand what's going on. And one of the exciting things about large language models is that potentially this could provide a new kind of front end to state-of-the-art AI, including machine learning. And that's what would make everything much, much more accessible, as in you don't need to code anymore. You just tell the large language model what you want, and it kind of figures out what is going on and what it needs to do. Of course, we are still quite far away from that in that most of the time it works, but sometimes it will break in horrible ways and it won't even notice and won't tell you. So there's still definitely the need for the human to know what's happening and what they're doing to be able to judge whether the result that they're getting is what they actually want or is going in a completely direction. But these are certainly exciting times, and I'm excited to see what happens in the next couple of, well, really, I mean, at the speed that we're moving, what happens in the next couple of weeks.
yeah, yeah, it is, it is. And I also wanted to add that I totally agree on that AutoML and that large language models can unlock even more possibilities to people to join it because I was one of those people who like I entered this AI data science world not that early, how to say, and I didn't know anything about like machine learning. Even I didn't know what is logistic regression, like linear regression, random forest, and all those things. And I had to manage a data science team, and I had to know the things really, really fast. And that time was ChatGPT revealed. And it wasn't available in Ukraine, but I managed to get an access using VPNs, and it was the thing that helped me to learn everything really,
Yeah.
really fast and understand what that code does, and like it is really unlocking for a lot of people, especially like me with more business background, to understand what it is, how it is working, and
Right.
translate it to human language.
Yes, yes, and especially in other disciplines. So for everybody who's not a computer scientist and who doesn't even really want to know all this stuff, which I personally don't understand, but okay, I mean, people are different, right? But you're interested in your application domain and you want to use AI because it potentially is going to be really helpful, but you don't have the expertise and you don't want to learn it because you don't have the time. You want to focus on your application domain. So in that context, there's really, really a lot of promise for large language models. And of course, we're seeing some of that being realized already.
Yeah, yeah, I agree. Um, So I think we can start your lecture. I see a lot of people already joined us, so I'm leaving stage to you. Just a couple words before we begin. We will have to our viewers. We will have first part of lecture. Lars will show us slides and tell like what is AutoML, how, when, and how is better to use it, and overall. I will share some insights on AutoML for us, and after that we will have small Q&A session based on everything that Lars showed, and after that Lars will show hands-on experience with some Jupyter notebooks on practical usage of AutoML, and during that it is also welcome to ask questions, and during that live demo, I'll say, we'll also go through those questions and also have a bigger Q&A session at the end of demo and everything. So that is our agenda for today's, and leaving the mic to you.
Perfect. Thanks, Timur. Okay, my slides are up. So very roughly, as Timur said, first I want to give you a little bit of a conceptual overview of a very, very small part of automated machine learning, because this has really exploded into a massive field, and there is way, way more going on than I can talk about in this format here. But I want to give you a little bit of an understanding of what automated machine learning is and what it roughly does, at least in certain contexts. And then we're going to zoom out, and for the hands-on demonstration, we will have a look at an actual open source AutoML system that you can very easily use, as I will show you, as something that you can take away and something that you can use immediately. Because on one hand, in this talk, I want to give you an idea of what AutoML is and that it exists, most importantly, and that you should be using it. But then I want to leave you with something that you can actually do, and not the, kind of typical academic talk where you have lots of ideas and you're like, okay, what's the next step? What do I need to do? Oh, hang on. So I'm trying to avoid that and leave you with something that will actually help you today and tomorrow already. Okay, so let's get started on this. Here's the big picture. As Timo already mentioned earlier, and as I'm sure you know if you have tried to do any kind of machine learning, this is pretty difficult. And it's not necessarily difficult because, you have to implement lots of algorithms, and you have to write really intrinsic code, and you have to do all kinds of other things, but because there are so many things already out there. And then for a given problem, you have to choose the right approach. And I deliberately put right in quotes here because right, and the definition of right, really depends on the particular context. This can be one thing for a particular data set and a completely different thing for another data set. Or even for the same data set that you want to use in different contexts, the right approach can be, again, completely different. And this is really where the difficulty comes from. And this is even what machine learning experts are struggling with, because, well, we can't keep up with everything that's happening in machine learning. There's literally thousands of papers published each year. It might be tens of thousands of papers, actually. And we can't keep up with that. So choosing the right approach is really, really difficult. And if you have ever tried to do this manually, this is really, really tedious. There's this kind of thing that you tell a student to do, and then they just quit because it is so tedious and they don't really get anywhere. So what automated machine learning attempts to do is to explore this space of possibilities for approaching a machine learning problem automatically and efficiently, and thus lowering the threshold of adoption. So as I said before, the idea is really that people who don't even necessarily have a background in machine learning or computer science can use these state-of-the-art techniques and get good performance for their machine learning models. So really that eventually, hopefully, anybody can use state-of-the-art machine learning, in particular these automated techniques. It doesn't mean that we're going to replace the human expert, because again, if you have done machine learning at all, you will know that it is very, very easy to get something that absolutely makes no sense. So you might be familiar with the concept of overfitting. This can happen, and there is no warning or error message, right? So you have to be really, really careful what you do, especially in this context here of automated machine learning. And while a lot of the tools that I will talk about towards the end do take care of many of these things internally, or at least try to mitigate the effect of them, you still kind of have to know what you're doing to then be able to take a machine learning model that comes out at the end and say that, yes, this is actually something that solves the task and that is suitable for what I have in mind, or, okay, I kind of have to go back to the drawing board for whatever reason and try something else. Okay, so here's a little bit more motivation. This is from one of our somewhat recent papers on just a bunch of different pre-provided ways in which you can connect different machine learning components. So the main thing I want you to take away from this is that this is difficult, right? There's a lot of stuff going on here. Don't necessarily understand what each one of these does, but essentially this is what you want to choose from. This is a small part of what you want to choose from if you're trying to model a machine learning problem. Not straightforward, and ideally you want to do this automatically. Okay, so let's have a look at how, at least at a very high conceptual level, we can do this. This is the simplest version of the problem I've just mentioned, algorithm selection. And this goes back to the 70s. Briefly put, given a problem, choose the best algorithm to solve it. And that is, of course, much more general than machine learning, and that is actually where all of this started out in the area of algorithms to solve hard AI problems. And then, well, we found that you can apply these in the machine learning context as well. But really, we have a choice of how we want to solve a particular problem, and this might involve training a machine learning model and then making predictions with it, or it might solving a hard AI problem, or indeed a combination of those, where I have to build a model that makes a prediction, and these predictions are then taken into consideration when I solve my hard AI problem, for example, a scheduling problem. And I want to identify the best way to solve this. A little bit more formally, and in the machine learning context, when we talk about automated parameter tuning or automated hyperparameter tuning, what we want to do is find a hyperparameter setting lambda star that comes from some suitable hyperparameter space, capital lambda here, such that we minimize the estimated generalization error of a model that is induced by this particular hyperparameter setting over a particular data set. This is one formulation. There's lots of different formulations out there in the literature. One of the issues with automated machine learning is that it's still a relatively young discipline, so it's really in the last about 5 years that this has taken off. And this means that even when it comes to the definition of the problem and the symbols that we're using for that, the community hasn't really converged yet. So depending on the paper you have a look at, you might find different symbols describing the same thing. But this is roughly what we want to do. We want to find something that has a good generalization error, which of course we can only estimate for a model that is trained using those particular settings. And this we can tailor to each individual data set and each individual scenario, as I've talked about before. So depending on what you want to do, this is going to be different. And in particular, we kind of want to move away from the classical way of doing this, where we really just have one hyperparameter setting that somebody came up with at some point, and we apply this to everything because it works well in general. And that might be true, but we're essentially looking for the delta in performance that we can get by moving away from this reasonable default that works for everything and going towards something that works better in the particular case that we're interested in. Okay, so here's the general approach. In general, for most of these approaches, we treat the underlying algorithm, so the machine learner that produces a model, as a black box function. We don't know what it does internally. We don't assume that we have any gradients. We don't assume that our meta loss function that we optimize is convex or anything like that. And that makes these approaches very universally applicable. So we don't need to know what happens. We're not making any assumptions about any kind of information that we can extract from this, and therefore we can apply it to pretty much everything. And this is one of the great things about these approaches, that essentially means that you can come up with an AutoML approach and you can apply it to all kinds of different things, all kinds of different data sets, for example, and you don't need to change it, customize it for any particular scenario unless you want to do something really special. So then what do we do? Well, we evaluate this black box function and we observe the effect of the parameters or hyperparameters without knowing the inner workings. So essentially we study this much like you might study a natural phenomenon. You can see that lightning is happening. you can't make the lightning happen yourself, but you can see that, oh, well, this tends to happen when there's clouds and there's rain and there's other stuff happening. And based on that, you build up an idea about the relationships of your black box, about what happens inside, and in particular, how you can tweak this to get better results. So based on what we observe, we then decide where to evaluate next. In particular, we decide what hyperparameter setting we want to evaluate next, and then we simply iterate that. So we have a loop that goes through different hyperparameter settings, observes how well they work, and then based on that, decides where to evaluate next. While we are doing that, we need to balance diversification and exploration, and intensification and exploitation. Essentially means that we need to get a good trade-off between going to parts of the hyperparameter space where we haven't been, so we don't know anything about it. It doesn't look like there's anything good there, but there might be. We don't know anything about it. Versus staying in parts of the hyperparameter space where we know that there's good performance, and we're trying to get that additional epsilon by very slightly tweaking the hyperparameter setting. So that's the typical balance that we'll have to strike there. And we'll have a look in a second at one of the ways of doing this in practice. One of the issues that always comes up is, well, when are we done? Because most of the approaches that are being used in practice are incomplete. This is simply because the space of possibilities is too large to evaluate exhaustively. If we could evaluate every possible machine learning approach for any given dataset exhaustively, this would be an easy problem, right? We simply do that, then we go through all of them, and we find the one that gives us the best generalization error. Done. But the problem is that we cannot do this. Even for kind of traditional machine learning, so if we're talking about tabular data and not deep neural networks where training an individual model might only take a couple of seconds, we cannot do this because we're talking about billions and trillions and quadrillions of different hyperparameter settings. So it's simply, the space is too massive to do this in any kind of comprehensive fashion. And that also means that we usually cannot prove optimality. So we get a result from an AutoML system, and that is a hyperparameter setting that hopefully is at least reasonable, as in it improves over whatever we started with, the default, or something that worked well in the past, or something along those lines. But we do not know whether this is indeed the optimal setting that we found there, or even how close it is to the optimal setting. It is entirely possible that if we invested more resources and essentially did more search in the space of hyperparameter settings, we would find something much, much better. We don't know. And there's no way to tell with these incomplete approaches and without doing a complete evaluation there. The performance of AutoML methods is highly dependent on the configuration space. In practice, most of these tend to be relatively well behaved in the sense that with a reasonable automated machine learning approach, you can usually get pretty good performance even with a relatively small amount of time. Of course, there could be cases where this becomes much, much more difficult, but in most cases, this is relatively well behaved. So in practice, when do we stop? We stop when some kind of resource limit is reached, or when the performance is good enough, or suitable definition of good enough. So this might be, the resource limit reach might be, for example, that you have run this over the weekend, and you come back into work on Monday morning, and you need a result now. So that's when you take what you have, and maybe you run something in the background to see if it improves, but you need a result at that point. Or similarly, if you run it overnight, you set this up just before you leave the office at night, and then you come back in the morning, you also need something to work with. So in many cases, the resource limits are dictated by the practical considerations of the particular application. Okay, so here are two very simple approaches to do this in practice. I've mentioned the one on the left-hand side already a little bit. Grid search, this is essentially where we do a more or less exhaustive evaluation. So we discretize our hyperparameter search space into a grid, and then we evaluate every possible point in this grid. Usually, we don't do this in practice because this tends to be really, really expensive. So this tends to be close to the exhaustive evaluation that we cannot afford, unless of course we discretize our grid very coarsely to make this feasible, but then we're really potentially missing a lot of good settings. So really, if you only take one thing away from this talk, if you ever do hyperparameter tuning, don't do grid search because it's not really going to work well in practice. Then on the right hand side we have random search, where we also have this space and we simply sample from it randomly. And this works surprisingly well in practice. Of course, most modern AutoML methods do better than it, but one of the nice things about this is that it's really, really easy to implement. You just need to define your hyperparameter search space and then you randomly sample from it. So that's a couple of lines of code, and it's also very, very easy to parallelize this, because now you can do the evaluations of your underlying black box completely independently. And this is really useful, for example, if you're doing something expensive like train and evaluate a deep neural network, and you do that on very distributed infrastructure. So, you have a cluster here, and then maybe you have some other cluster somewhere else, but you don't necessarily have the network connectivity between them, so that you can kind of run something in a very distributed fashion. With a random search, you can very easily work with this by just generating the points in the space that you want to evaluate and then distributing them across the machines and doing the evaluation without the need for any communication while this is happening. So this is a really nice and simple method that often gives you surprisingly good results in practice. Now, of course, we want to be more intelligent when we do this. And one of the state-of-the-art methods, probably the state-of-the-art method still, is model-based optimization, where we take a small number, full pseudo definitions of small, of initial configurations. These could be random, or this could be a Latin hypercube design or something along those lines. And we use those initial evaluations to build a first surrogate model of the parameter or hyperparameter performance surface based on these evaluations. So essentially, the way model-based optimization works is very similar to what you do as a human, where you do a bunch of evaluations, you observe what happens, and you build up a mental model in your head of how tweaking certain hyperparameters affects the outcome that you're interested in optimizing. Here, the same thing happens, except we're using machine learning to build this mental model, and we call this surrogate model here, but apart from that, it works pretty much the same way. So then we have the surrogate model, and we can use that to predict where to evaluate next. Because while searching this hyperparameter space across the black box that we want to optimize is expensive, doing it across our surrogate model is really cheap. In the same way that you can ask your mental model, hey, should I be doing this or should I be doing that? And you get a quick, approximate solution. I think that would work. I think that's not going to work. Don't try this. Same kind of idea with a surrogate model. So essentially, we have something that's more intelligent. We now have an explicit model of how the hyperparameter settings affect the outcome. We search over this surrogate model, which we can do very quickly because we really just get a bunch of predictions from a machine learning model. And based on that, we decide the point to evaluate next, the most promising point where to evaluate next. We do that. We get another evaluation of our black box function, and we feed the result of that into the next iteration of this process. So we built a new surrogate model, which now takes an additional point into consideration. So we're refining and updating and hopefully making the surrogate model better over time. And we again repeat that and stop when the resources are exhausted or we have achieved a desired solution quality. So for example, an accuracy that we're looking for or something like this. And this allows a much more targeted exploration of the promising configurations than certainly the random search that we talked about before, because instead of doing this completely randomly, and in particular in a non-adaptive fashion, where we're doing the same thing regardless of what we observe, which is kind of, counterintuitive, you wouldn't do it as a human, we really get the process to think, in quotes, about what worked well, and based on that, what might work best going forward, and then really explore that in a very targeted fashion. Okay, so this is kind of a picture of how this works at a high level. So we have this loop there on the inside that goes back and forth between the process that we want to evaluate and the surrogate model, feeding the information that we observe from that to the surrogate model and proposing the next hyperparameter configuration to evaluate. Input to all of this is really just the hyperparameter space, and then some of course we need to tell it how long we want this to run, and then the output of this would be a hyperparameter setting that is the best that has been observed in this particular context. All of this is a little bit abstract. Let's have a look at an example to see how this actually works. Here on the top panel, we have the solid black line. That's the function we want to optimize. This is what's unknown in the black box setting. So here, for the sake of being able to show this, I have drawn this. This is essentially how the hyperparameters affect your machine learning model. So this is what we don't know. And here, this is this quadratic function overlaid with a sign. So we get something that is not super boring to optimize, but that we can still do. Then we have a couple of points that we have evaluated initially. These are the red circles. And you can see that these are kind of evenly spaced in our kind of boring one-dimensional parameter space here. So again, you can do this randomly, or you can do it evenly spaced or something like that. It really doesn't matter all that much. What does matter is the dashed black line. That is our surrogate model. So that is the function that we have fit to the values that we have initially observed. So here to the red circles. And the first point after that that I've included here, the green square as well. As you can see, it goes through all of these points. The gray shaded area around the black dashed line is the uncertainty of the predictions. And we can see that the further we get away from observed data points, the larger this becomes, exactly as we would suspect, right? The further we're away from data that we have observed, the less certain we are about the outcome of this. And as you can see, this is not a particularly good approximation of the underlying function. While it has a couple of points, it is in particular missing the point that we're really interested in, the minimum here. So we're minimizing this function. We essentially want to find the point for our hyperparameter setting x of 0, where we're minimizing the output y here. So our initial surrogate model is not particularly good, but as we will see, this is actually perfectly fine. And because we're running this in iterative fashion, we will still get a good result in the end. At the bottom panel here, we have the value of the expected improvement function. So this is what we're using as an acquisition function here. This is essentially what tells us how good every point in my hyperparameter space is with respect to improving the result, the best result that I have observed so far. And as you can see here, the peaks for this function are around the best point that we have observed so far. So this would be around x equals minus 0.4 or something like that, which also kind of makes sense. So again, kind of similar to what I talked about before, this would operate very similarly to what you would do as a human. You evaluate a bunch of points, you see that something works well in this region here. Okay, so let's have a closer look at that, right? Let's explore around the points where we have observed good performance and not immediately go somewhere else where we might find something better. Okay, so let's step through a couple of iterations here and see what happens. The next proposed point to evaluate is the blue triangle there. So this is close to the best point that we have seen so far. And this, of course, coincides with the maximum of the acquisition function in the bottom panel there. So we evaluate that and we find that our prediction was actually pretty good, right? So our surrogate model hasn't really learned much in that respect. And in particular, we have found that the value is not as good as of the red circle next to it. So what we're doing now is we go the other way, right? So we have a look in the other direction of our one-dimensional hyperparameter setting to see if we can find something better there. And again, the prediction is that it is not going to be better than the best value that we've observed so far. But if you look at the gray shaded area, the bottom part of that is actually better. So that essentially means that the model doesn't think that there is something better there, but there could be, because it is not 100% certain about that value. We haven't observed any data at that particular point. So then we do this, we observe the next update, and we kind of have a similar situation to before, where our prediction was pretty much accurate, and we have found something that does not improve. And at this point, the model is also satisfied that in this particular part of the hyperparameter space, we're not going to find anything better. We have the red circle, which is our best point so far, and we have points to the left and right of it that are not improving, that are worse. So, okay, it's unlikely that we will find something better there. And now something interesting actually happens, because the model now essentially goes off to explore. It goes into a part of the hyperparameter space where we haven't done any evaluations. And its prediction there, so again, this is the black dashed line, is not very good. It's predicting that we will find something there that is not as good as the best point we have observed so far. But the uncertainty is also very large. So this is the point where it says, I'm going to go there. I don't think that there's anything good there, but there might be. I really don't know much about this particular part of the hyperparameter search space. And again, you can see that this point, of course, coincides with the maximum of our acquisition function shown in the bottom panel there. In this case, it turns out that we were actually lucky, and the prediction of the surrogate model was really quite bad. And here we have now ended up very, very close to the actual optimal point. So here you can see that the update for our surrogate model did actually change the predictions quite a bit in that part of the hyperparameter space, because again, the earlier prediction was quite incorrect. And based on that, we are now going to do exploitation in this particular part of the hyperparameter space. Essentially the same thing as before. We have found a new best point. We're going to look in the neighborhood of that new best point, whether there's something better there. So this continues for a couple of iterations here. We look to the left, we look to the right, and we find that, yeah, okay, we can't really find anything that improves there. Then we go a little bit further away, and we find that, yeah, okay, that also wasn't better. And again, we kind of search in that neighborhood again. So very similar to what you might do as a human, where you're looking at small changes to see if that would actually get you an improvement. And here, the last iteration that I want to show you for this, at this point, the model has decided, or the process has decided to start exploring again. We have now kind of very comprehensively evaluated the neighborhood of that best point that we have found, and the model is pretty certain that there's not going to be anything better in that particular area. So instead, we're again starting to explore and jumping to a completely different part of the hyperparameter search space. So you see the blue triangle here in the top right corner. Of course, this will not give us a good value, so I'm stopping this demo here, but you get the idea, right? So, and of course, all of this happens automatically. So I, for the sake of explaining what's happening, I have used phrases like, you know, we're starting to explore, and we're doing this, and we're doing that. But this is not the user telling the process to do this. This all happens automatically by suitable choice of acquisition function in particular that trades off this exploration and exploitation. Okay, if you want to try this yourself, here's a very simple example that you can find at the URL at the top of the slide here. And there's also a Google Colab if you kind of want to do this live on one of the next slides, because fundamentally this process is very, very simple. So if you wanted to do this yourself without using any AutoML systems or without any libraries, here's one way of doing this. A very simple task. I'm having a look at tuning the hyperparameters of a support vector machine here on the iris dataset, and I'm doing this by essentially exhaustively evaluating over this relatively small hyperparameter search space on the surrogate model. So the key thing here is really that we build up the surrogate model, and this is what happens on the next slide here. I'm using a random forest regression model as my surrogate model here. So I'm doing a bunch of initial evaluations. I'm fitting the initial surrogate model, and then I'm searching over the surrogate model to decide where to evaluate next. And this is a really simplistic implementation that doesn't even take the uncertainty of the predictions into consideration, just to illustrate the concept and to give you an idea of what's happening. I don't want to spend too much time on this. You can have a look at this, and feel free to send me an email if you have any questions about this. So here's slide 3 of my 2-slide MVO, where you can see the output of this, and you've got the URL there for the Google Colab, where you can play around with this yourselves. All right, almost done with this part. I just briefly want to mention that as I said at the beginning, the whole area of AutoML is much, much larger than what I talked about here and what I can talk about here. I want to, in particular, talk about AutoML in the context of deep neural networks, where in addition to hyperparameter settings, there's also the question of the neural architecture. And this is kind of a much more difficult problem because on one hand, it is much more expensive to evaluate. So training a deep neural network is much more expensive than training a support vector machine, for example. But also because we're talking about a qualitatively different search space. With a hyperparameter search space, it might be very large, but at least you know exactly what it looks like. There's this hyperparameter and has this possible range of values, and there's these interactions and conditionals with other hyperparameters. And that might be very big, but I can define this. With a neural architecture, I can always add another layer. I can always add another neuron here or another connection or something like this. So our search space is unbounded. I can't exhaustively explore this because, well, it's unbounded. Even if I have infinite resources, there's always more that I can do. So in practice, what we do to get around this is that we rely on building blocks, sometimes called motifs or similar things, to essentially assemble a deep neural network from components that are smaller than the big network but are larger than individual neurons or individual layers. And there, popular methods for doing this in practice are also evolutionary methods or reinforcement learning, and not so much Bayesian optimization, although you can apply this there as well. And in some cases, for example, for the DART system, we're going away from this black box assumption and actually get gradients that then allow us to converge faster on a suitable neural architecture. Just to give you a very brief glimpse of this, there's obviously much more to this that I'm not going to get into here. Here are some tools and resources. There's a long list of AutoML systems. Here's my somewhat opinionated selection of this. So there's AutoScaLearn, AutoPyTorch, and AutoGluon, which we're going to have a look at in a couple of minutes in the hands-on demonstration. And then there are various commercial offerings that are essentially easier to use because you get a nice integration, for example, with the Amazon cloud or with the Google cloud, where in many cases you don't even have to write any code, but you just put your components together. And with most other AutoML systems, you still have to write at least a little bit of code. And again, we'll have a look at that in a second. Here's some further reading. There's lots of literature on this. So the first paper here is kind of the seminal paper for Bayesian optimization, for this model-based optimization that I talked about earlier. Now quite old, more than 25 years. Then there's a recent paper on hyperparameter optimization in particular. And there's also a survey of automated machine learning frameworks. Then just about a year old now is a survey of neural architecture search with insights from 1,000 papers. And these 1,000 papers are from a time span of about 2-3 years. So a lot of stuff is happening there. Just something to get started. Again, there's a ton of literature out there and lots and lots more material. If you want to know more, we have an online class on this. This is on AI Campus. It's completely online and completely free. So we have videos, we have slides, we have exercises for this. You can find it at the URL on the screen there. This goes into much more detail on everything related to automated machine learning. The course is somewhat dated now, so we did this originally in 2019, and we are currently in the process of revising and extending this, so this will hopefully come online later this year, but we don't really have a fixed timeline on that yet. But for now, you can find a lot more information here. If instead of that you want to read a book, there's also a book called Automated Machine Learning, also published a couple of years ago. So this is not the current state of the art anymore, but it's a nice book to give you an overview of the area and some of the systems that are being used and how they work internally. And this is also available for free online. So the book is published by Springer, but it's open access, so you can just get a PDF of the entire book. Okay, and with this, I would like to break here and see if there are any questions on the conceptual part, and then we can move on to the hands-on demonstration with a Colab notebook and one of the AutoML systems, AutoGluon.
I don't see any questions right now from the auditory, but okay. I have a couple questions from my side, so maybe it will bring new questions from the people. So first of all, I want to start with newbie question. So comparing to like artificial intelligence as people know it, like ChatGPT or Bing or I don't know Bard if someone used, how is it different to AutoML and how it is relate to AutoML at all?
Yeah. So, of course, I mean, technically we don't know that because, well, OpenAI and Google and various other companies don't really tell us what exactly they're doing, but they're almost certainly using some kind of automated machine learning under the hood to train these large-scale systems. Because things like hyperparameter optimization, I mean, way back when I did my PhD, this was not a thing. Nobody did it. And nowadays, it's really, you have to do this, right? This is kind of the first thing, one of the first things that you think about. How can I optimize this further? Do I really have the best approach here? So what I talked about here is really what happens under the hood for most existing machine learning systems, I would say. I would be surprised if there was a company with a product that includes machine learning that is not doing hyperparameter optimization, because nowadays it is so easy to do, and often this can really give you much better performance essentially for free. It's really just machine time that you invest in that. So that would kind of be the relationship, or at least on a very high level and in about a minute here. Of course, in practice, this is much more complex and much more difficult. But fundamentally, you can think of this as this is kind of what happens at the lower level when we talk about training these complex systems like ChatGPT, for example.
Got it. We already got some questions, but I also wanted to add, let's start from the questions. But one moment, I wanted to add one more from me, if you let. So imagine I'm trying to develop maybe some price prediction model for real estate, and as far as I remember, I'll have to prepare a huge data set, label it, then run some experimentation, leave my computer for a while, then evaluate tests, find some best parameters, and do it again and again and again. And like I understood that AutoML took away from me that some part of repetitive work and finding something, so it can run experimentation. But in the terms of preparing then data set for that, is it somehow different in that approach or not?
Well, fundamentally, it's exactly the same as what you would do without automated machine learning. In practice, AutoML tends to work better if you have large amounts of data, just because it essentially has to evaluate multiple alternative settings in a statistically rigorous way, and that means that essentially we have to subdivide our entire data set into training and testing and subdivide it further so that we end up with smaller and smaller amounts of data. But fundamentally, you can apply this to any existing data set, and what it really does for you, it takes away this experimentation of, with this data set, what is the best modeling approach? So that is what, at least the aim is, that all of this happens automatically. Now, that said, techniques that we use in automated machine learning, so for example, Bayesian optimization that I've talked about before, can also be useful in the context of active learning or data acquisition. So for example, you have a data set and you have the option of getting more data, but this is expensive. So you want to know, what data should I get in order to help the model most, in order to help the learning process most. And you can apply Bayesian optimization in pretty much exactly the same way, where you're searching over the space of possible data points. And then what you get is essentially also, it's very similar to the demo that I showed, that your model can tell you that, hey, this data point here would really help me because I don't know anything about this part of the space of the underlying possibilities. So you can use similar techniques in an active learning context where you're kind of building up your data set with the help of machine learning, because you don't, or you can't afford to just get tons and tons of data because it is too expensive.
Got it. Interesting. Okay. Thank you very much for the answer. And also we got some questions from Jod D. First question is, it's thank you for interesting presentation. Could you please share with us a little bit of insight or tips on how to apply the automated ML concepts in research problem?
Yes. So, well, this depends on what kind of research. So let me answer this in two parts. First, if your research is not in machine learning and computer science, but you want to use it in order to further your own research, as in you want to apply machine learning, but you don't necessarily want to advance it, my advice would be just use an AutoML system. For example, AutoGluon, which we're going to have a look at in a couple of minutes, because this will take away some of the tedious work, and it is also a very easy way to get better performance for your particular application in the end. If you are talking about research in machine learning, then this becomes a little bit more difficult. Of course, AutoML is not a solved problem. So this has, as I said, hasn't been around for that long. It's still a relatively young area. And while we have been able to make lots and lots of progress there, and the area has really kind of exploded over the last couple of years, there's still lots and lots of things to do, in particular in the context of deep neural networks, because one of the challenges there is that getting data points, getting data to base our optimization on is extremely expensive. And then there are concepts like multi-fidelity optimization, where essentially we don't train a model to completion, but we train it a little bit and see how it might do if it were to be trained fully. And based on that, we might already be able to say that, oh, this is not going to work out. We don't need to continue with this. But there's lots and lots of scope for research in AutoML. For kind of research in machine learning without the automated part, I would say that AutoML is very exciting in the sense that you don't really have to come up with machine learning approaches that are very general anymore, because the kind of traditional approach to, I want to develop a new machine learning algorithm, I would try to make this work as well on as many things as possible, right? Because I want this to become the new state of the art. But with automated machine learning, I can develop something that is really a very niche approach that only works for, let's say, very highly imbalanced data sets with missing values, and only in this particular context. But if I now put this into an AutoML system, the user can get the benefit of my new method without even necessarily understanding how it works. So I think that this is very exciting in the sense that it enables researchers to really go deep on a particular problem and develop specialized approaches, but then not sacrifice overall performance, because we can just put everything all together in an AutoML system.
And I just realized that Jody provided some context to the first question, so I'll read everything. So maybe he speaks on something different. So in terms of previous question, she added that when working on particular paper, it is a lot of questions, but I read all of them and I understand that all of them are connected. So when working on a particular paper, there are many possible high-level solutions can go with, and then those solutions have many possible individual hyperparameters. And you have touched upon this problem in neural architecture and pipelines, but high-level solution choices go even beyond network architecture blocks. And for example, to add more practical context, we are working on a method for extracting the weights of GNN models hidden as black box behind an API interlocal copy. And one can think about this problem as knowledge distillation to a local student with only having access to the output of the teacher and no access to the teacher's weights and architecture. And in this problem, one can with many different distillation designs and loses each with many individual hyperparameters. And could you please suggest how to approach such research problems with automated ML?
Yes. Well, okay, that's a very big question. So let me, my kind of 30-second take on this. But in general, I would advise that whenever you have a choice of how to approach a problem, don't make that choice. And code it in some way that an automated system can explore the alternatives automatically. So really don't commit yourself to any particular approach, evaluate all of those different approaches. Now, in particular for the problem that you mentioned, I think the challenge is really going to be how to evaluate the results. Because in many cases, it's not as straightforward as simply saying, oh, accuracy is 70% or something like that. But there are many, many more things that you have to take into consideration, in particular if you want to be statistically rigorous, and in particular in a context like this where you're kind of trying to reconstruct a model behind a black box API or something like this, where really what do you even mean by this? Do you want a faithful reproduction of the model itself, or do you want to kind of functionally reproduce the model in terms of achieving a similar accuracy on a particular data set? But then how do you choose this particular data set? Do you want to do this over a number of data sets? How do you take the standard deviation of your accuracy over those data sets into consideration? So it sounds to me like in this particular context, the challenge is really going to be to define how you evaluate the quality of a solution, and not even necessarily iterating and exploring, searching over these different alternatives, because it sounds like it's a relatively small number of alternatives. But yeah, so as with all machine learning, the evaluation is really one of the most challenging aspects in practice.
Okay, got it. Thanks. And I don't see any new questions, so I think we can move to the collab.
Okay, great. How are we doing for time?
I think we have time. So
okay, good. Right. So I will start with the first collab here, and if we can just bring up the slides very quickly, because on the next slide I have links. So if you guys want to follow along, or if you want to have a look at this afterwards, I've prepared 2 demos for this. We probably will get through only one of these, but that's what we'll be having a look at now. Okay, let me switch to the first collab here, this one. So here I'm using a particular AutoML system called AutoGluon. This is open source, developed mostly by Amazon. But it's a Python framework, so you can install this using pip, and this is exactly what I've done here. I've done this earlier because, well, you can probably see this, installing everything that was required here took 6 minutes, so I didn't want you to wait and stare at a package installation, but you can easily do this yourselves. Okay, so let's scroll down here and have a look at what we can actually do with it. So loading the library here, I've also done that before because that takes a little bit of time. And I'm taking one of the example data sets from the AutoGluon website here. So we'll have a look at this in a second. You can, of course, do this with your own data, but the demo that I'm showing here is based on one of the quick start examples on the AutoGluon website, so that you can easily get started with this yourselves as well. So we're getting some training and test data provided by Amazon for this particular example. Here's what this looks like. So here I'm printing the first couple of rows in my tabular data set. So this is a problem where we essentially want to predict the income of a particular individual that is described by a number of features, like the number of years they were educated, the highest degree, marital status, native country, and so on and so forth. And the prediction task is just binary here. So we want to predict whether they make less than or equal to 50K per year or more than that. So relatively simple problem and a relatively small data set, just for the sake of showing you something. But you can, of course, use this for any data set that you like. So here, I'm just printing a little bit more information on the data set itself. So you can see the number of observations that we have here. So this is just under 40,000. So, a reasonable amount, but certainly not a large data set. And then some information on the distribution of the individual feature values here. Okay, so let's actually start to run some AutoML on this. This will take a couple of minutes. So I will talk about this while it's running. So it's really just this one line of code here. I'm creating a new tabular predictor. I'm telling it what the label is that I want to predict, and then I tell it to fit based on the training data that I have gotten earlier. And now we can see that a whole bunch of output is starting to happen here, so that this is what AutoGluon gives us if we run it. A little bit of information on the system and a little bit of information on the data that we're working with. And AutoGluon runs relatively quickly, so this will only take a couple of minutes. And essentially what it does is take a bunch of existing learners, let me scroll back up again here, and try these with different hyperparameter configurations. So in particular, in the kind of default version that I'm using here, and of course you can make this almost arbitrarily complex, so you can find more information on this on the AutoGluon website. It doesn't really do any hyperparameter optimization as such, because this is a really, really expensive thing that I cannot do in, or at least I cannot do well in a couple of minutes. So instead it takes a bunch of different learners. So you can see here, looking at the output, we have a k-nearest neighbor learner, we have a light GBM, so we have a gradient boosting machine here, we have a random forest, another random forest, we have another boosting model, we have the extra trees model here with hyperparameter settings that worked well in the past on a reasonably large range of machine learning problems, and we just tried these different ones. And then we find the optimal over all of these. Roughly speaking, we'll see in a second that it is slightly more sophisticated than that. But really, what this is doing is what you would do as a human if you just wanted to get a feeling for how difficult a particular task is. You have a look at, you know what worked well in the past, right? You're a machine learning expert, you have done this before, you know a bunch of approaches that work really well, and now you're applying those approaches on your new data set, and you're trying all of them because you don't really know which one is going to work well. But it is relatively quick to do this, so it'll just take a couple of minutes here, and that will give you an idea of what works well and what doesn't work well. In particular, it also gives you a reasonable starting point. So this might actually be where you stop, right? Again, depending on what the performance in the end looks like, but this might be all you do. And after this, you have already found something that you can work with, and you don't need to do all this expensive and complex hyperparameter tuning that we've talked about before. And that's kind of the one of the main ideas behind AutoGluon here, that you get something that is quick, and you can just run this almost interactively, right? I mean, you see that it's not quite interactive. It does take a couple of minutes, but it's just about enough time to go and make a cup of coffee, for example, and then come back and you have a result. And you don't need to let this run overnight or over the weekend, and you don't need to let this run on a supercomputer or anything like that. So here, this is just running in the standard Colab. You can obviously also run this on a laptop, and you will also get reasonable results there. Depending on, it might take a little bit longer, but we're still really only talking about minutes and not hours or days. And while this is running, you can kind of get an idea of what's happening already. So here you can see the validation score, in this case accuracy, for the different models that it has tried. And you can get a feeling for how well this might work in practice, right? So here we're getting relatively high accuracy scores of, you know, around 85%. Okay, here we've got 88.5%, and now it is actually done. The last thing it did here is fit an ensemble model. And this is essentially something that you get for free when you run this kind of hyperparameter optimization, or you try these different alternatives, because you know what the predictions were, and you can then compute, if I put all of these together in a certain way, would I be able to do better? That's the idea behind this. So we're building an ensemble, or AutoGluon is building for us an ensemble of a bunch of these different models that it has evaluated before, and weighting these with different weights that it's giving you here, depending on the quality of the predictions. And as we can see, this is overall getting a better accuracy here, 88.88%, which is higher than at least all the ones I have on my screen here. And then returning all of this as a predictor. Now, this predictor that I get back, I can use just like I would use any kind of other machine learning model in scikit-learn. So when I run this here, I can make predictions on my test data. This works exactly as expected, right? So for the 9,769 rows in my test data set, it gives me the prediction of which income class the model thinks that particular person will fall into. And that makes it very easy to integrate this with your own code. So you don't need to write a lot of code around this to then take the result of your AutoML run and do something with it to extract the model, which you can then actually use, etc., etc. You can use this just like you would use any other model in many cases. Of course, in some cases, it won't work exactly the same way because there's something very different under the hood, but in many cases. In addition to that, you can get additional information about what happened there when it ran. So the predictor has this function called leaderboard, and this allows you to get the performance on a data set that I pass in as an argument here of the different things that it has tried. If we have a look at this, we see that the overall best one, hang on, let me get this right here, is the weighted ensemble as we had a look at before. So this would be the 88.88% accuracy here. But you also get the scores for all of the other models that were evaluated. So you kind of get an overview of the different approaches, and that might give you some more information about the difficulty of your task here. So in this particular case, it doesn't look like it's really all that much variation that I'm getting, apart from maybe the k nearest neighbors, right? So these aren't really as good as the other models that were evaluated. But apart from that, everything is pretty close, and we're getting a pretty good accuracy with all of these. Now, in addition to doing this on the test data, which is what I've done here, I can also do this on the training data. And okay, this will take a few seconds here. This will give me, as we will see in a second here, something that looks somewhat similar, but is not exactly the same. There we go. In particular, we're getting evaluation scores here that are, well, for the test score, they are higher, as we kind of would expect, right? So it does better on the training data than on the test data, but we also get a slightly different ranking here. So we have different approaches that are now in the top performers here compared to the testing data set. And this can be important if you want to check for overfitting, because of course, again, just like in normal machine learning, we want to make sure that we end up with a model and a modeling approach that works well not only on the particular training data that I've given it, but really on the underlying distribution. And this can be a nice way of checking that this is actually the case. I can also then have a look at a little bit inside of what happens in AutoGluon here and actually plot this graph of the weighted ensemble that it came up with. So this is just really a nicer representation of what I showed you earlier. We have the individual components of the ensemble here at the bottom with their individual accuracies and then the overall accuracy, and you get a little bit more information about how long it took to fit this and how long it took to make predictions with this. And if you look at this, you might see that, well, you know, the neural net fast AI learner really took much longer than everything else. So if I'm interested in being able to train a model quickly, I might want to remove that one member from the ensemble to get something that is hopefully very similar in terms of performance, but much faster in practice. And again, in the AutoGluon documentation, you find much more information on this, and it's much more flexible than what I'm showing you at the moment. So there's lots of scope for you essentially to go in there as a machine learning expert and kind of nudge it in a particular direction, because again, maybe you're, for example, interested in getting a model that is particularly fast to train, or maybe you're interested in getting a model for which it is really fast to do inference because you want to deploy this on an edge device, and you can adjust all of this to your liking in the AutoGluon system. Then also important, you can ask it for model failures. In this particular case, we don't have any, but this can be really important, in particular if you find that on a particular data set a learner was not chosen or does not give you good performance. Well, was that because it simply always failed? Maybe it ran out of memory or something like that. Really important to know if you're doing this in an automated setting. If you're doing this manually, of course, see it. But if you're running an automated system like AutoGluon, all of this is abstracted and you can't really see what's happening under the hood while it's running, but this then gives you the opportunity to inspect this. Okay, then for just to show you a minor variation of this, I can specify a time limit to autoglue on here, because maybe I only have a minute. So I give it 60 seconds here. I don't want to wait the almost 4 minutes that we waited up there. So instead, I'm going to run this with a time limit of 60 seconds. And as you can see, the output is very similar to before, but we now have information on the remaining time. And this will actually finish after approximately a minute. Not so much important for this particular demo here, but imagine you're working with a really, really large data set, for example, and then you might want to limit this to, say, a couple of hours instead of waiting for days and days and days, because some of the fits take really, really long, as we have seen for one of the models in the ensemble earlier. Okay, so this will be done in about 15 seconds here. And the result of this is very similar. So here, actually running this for 4 minutes instead of 1 minute didn't get us that much. We still got the ensemble model with a very similar accuracy score here. And then we can again use this in exactly the same way. So I can get the leaderboard here as the only thing I'm going to do to inspect the accuracies of the individual runs here. So you can use this in exactly the same way as before, and you can also again plot the components of the ensemble here to get an idea of what's happening. And now we indeed see, if you look at the bottom row of the yellow boxes here, you see that the particular learner that took a long time to fit earlier, more than a minute actually, so more than the time limit for this entire AutoML run, is not part of our weighted ensemble. But it also turns out that we can actually remove this without really impacting the score in major ways. So, just to give you a glimpse into the kinds of things you can do with AutoML systems and the ways in which you can customize these to get something that works in your particular context. Okay, so this is all I have for this first notebook. Are there any questions on this?
I don't see any questions on this one. People, if you have any, it is the best moment right now to ask anything that you got during that notebook. So let's wait for a couple of seconds if maybe anyone will ask something.
Okay, I will stop the sharing for now so that then I can move to the next notebook.
Yeah, but as I understood, it is like so your model is not deciding instead of you like what to use in terms of should be some decision tree or like linear regression and things like that. It is only helps to evaluate like for specific algorithms that you decided to use different, I don't know how to better call it, frameworks like XGBoost, scikit-learn, and other. So you can evaluate performance of each of them and choose what works best for you.
Yeah. So, and in particular, in this kind of formulation of the AutoML problem, we can treat the choice of the modeling algorithm. So XGBoost versus maybe a k-nearest neighbor learner or a linear regression or something like that as just another hyperparameter. So this just becomes part of this space that we're searching over. Now that said, if in particular cases you really want to limit it to XGBoost, for example, or you want to limit it to a decision tree because you want to be able to have a look at the model and then at least try to understand what it does, you can do that at least with most AutoML systems. So that this kind of depends on the system, and it is not necessarily super easy to specify this, but you can limit these systems to only search certain parts of your hyperparameter space, including the choice of algorithms. So if again, you want, for example, you wanted to limit it on to things that run relatively quickly and that don't consume a lot of memory. So in particular, we want to exclude deep neural networks because we want to run this on a Raspberry Pi or on some kind of embedded device on the edge where we don't have these resources available, then you can definitely do that as well.
Okay, got it. Thank you. So we have no new questions. I
Okay.
think we can move forward.
Yes. So then let me show you the second demo that I have prepared. And this is really just for the sake of completeness because I have shown you the... Oh, great. Okay, runtime disconnected. Well, that's not good. Okay, so this is the same kind of demo with AutoGluon, but this time for image data. And because this really does take quite a long time to run, I'm using a GPU runtime here, but even with that, it does take a couple of minutes. I will just go through the output that I've generated earlier. There's a link to this collab in the presentation, so you can feel free to play around with this yourselves. So we're installing the packages here, and then we're importing everything. We're also, again, using a example data set that is provided by Amazon. So this is, again, based on the quick start guide on the AutoGluon website. This is what our training data looks like. So we have a path to an image and we have a label for that, as you would expect. So if you have done any kind of image classification with Python before, then this will look very similar. These are the kinds of images that we're talking about. So these are clothes, essentially, that we want to predict a category or a class for. And then we can use AutoGluon in pretty much exactly the same way. So again, one line to instantiate this. Instead of the tabular predictor, I'm using the multimodal predictor now. And as the name suggests, this is not limited to image data. So you can really use this on any kinds of other data. I've as an example here, used the image data, but you're not limited to that. And apart from that, it's really exactly the same as before. We're giving it the column that contains the label that we want to predict, and then we tell it to fit this on the training data set that we have generated earlier. As I said, this takes some time, so I have done this earlier, and I will just show you the output here. Looks different to before because here we're of course fitting a deep neural network, but fundamentally a similar thing happens to the tabular data case, where we don't do a full hyperparameter search or even a neural architecture search because this would be way too expensive in the default case. And you can do things like that as well, but it doesn't do it by default. But instead, it essentially tries something that has worked well in the past. And yeah, so we have a bunch of output here where we have trained the model. It gives you a little bit of information on how you can load this separately, so you don't, if you now wanted to use this in a different context, you don't always have to rerun the AutoML process, but you can, just like any other Python scikit-learn model, you can save this and then load it in a different context and come back to it. And again, we can use this exactly like we would use any other kind of machine learning model in Python. So I can call the prediction button and give it some test data, and this will give us the predictions for the individual images, in this case, in the test data. And then as the last thing, I can also, I don't have a leaderboard here because we have really only the one approach for the deep neural network that was tried here, but I can get it to give me some information on what happened during the fit, in particular the accuracy that was achieved. So here we are at 98 point something %, so really pretty good, and the training time that was used for that in seconds. So as you can see, it did take a little bit of time, but in the context of training deep neural networks, this is really not that long at all. Of course, we're working with a small data set here, so if you're doing this on your real world data, then you might see something that takes much longer, and in that case, it might be necessary for you to tweak how exactly AutoGluon runs. I refer you to the API documentation for that, which is very extensive, and there's also lots of examples that you can find on the AutoGluon website. Okay, are there any questions on this notebook here?
I don't see any. I don't see any new questions right now.
So
let's
let
wait maybe for a moment, and new questions will appear.
Okay, and yeah, so then I have stopped the sharing again, and at this point I'm happy to take any questions on anything that I have talked about.
Yes, for now I don't see anything new, but from my side it was quite interesting.
Thank you.
And personally, I get a lot of new knowledge, and it is definitely something new for me to try and to play a little bit with the notebooks that you shared. And by the way, we'll add links to those notebooks after the session,
Fantastic.
so you also can play around with everything. And yeah, we have only grateful messages.
Thank
Yeah,
you.
that everything is concise and examples were very good.
Okay, perfect. And if anybody has any questions after this, feel free to send me an email. I'm happy to talk further. In particular, as I said before, this is a massive area, right? And we're really we have barely even scratched the surface of this. So there's a lot more. And if you take anything away from this, you should be doing automated machine learning in practice, because as I've shown you in the notebooks, it's really, really easy.
It is. I agree. Then I want also to highlight the topic of the sorry. I wanted to highlight the topic of how important it is to donate if you have ability to do this. And here you can see a little QR code which you can use to send some donations that will go directly to the reactive post. And yeah, thanks again, Lars, for that great lecture. We will also post it in YouTube after this, so other people can look it, or attendees can also watch through it again if there is need. And I wish you a very nice rest of the day, and thank you again.
Thank you very much. The same to you. My pleasure to be here. And thanks again for the invitation.
Bye.